Shut up, actually, these are viable sources.
What? What is that? I'm sorry, I didn't my glasses. What did I say about the meter stick? We assume the meter stick is.
This would be the 5.17 and this one's 2.23.
What's applying the normal force?
So like 5.17 means it's the weight of the hanging mass, and then
Oh, you gotta
the
add.
stick, and then the normal force would go would add. I'm not sure.
And then we just.
Oh, that's the
Yeah, don't put the stand in your diagram, otherwise I think it's let's see here. Kim, pick another force and put it on the board. Go.
Yeah, I probably shouldn't have drawn the ring of this. The ring thing. Oh god. February 9th, 3 to 6, team bonding. What?
Okay.
Yes. Yeah, because I already don't spend enough time in quad every day.
Put a different force up in that one.
We all just chant.
Shut up. That's disgusting. You would not say that. I don't believe that for a second.
Okay. Okay, let's see here. Michael, put the third force on the board.
I believe in you, Michael. Thanks, Patrick. I'm not. Did you hear what Max was saying? At the team bonding.
What do you say?
We're gonna do meditation.
Team bonding February 9th.
I am not.
And we're starting out with
Meditation's
relaxation
awesome.
and mindfulness meditation.
Meditation alone is
Like-
awesome.
like Michael.
I do not want to meditate with other people. I refuse.
Okay, so
Student psychology.
look at what we've got on the board. I would have put F with the subscript in rather than the other way around, but okay. So we have the normal force, we have the weight of the hanging masses, and we have the weight of the meter stick, all up there. So are there any, is there anyone who needs to explain how all three of those forces were arrived at? We got all three forces okay?
Yeah.
All right. How about look at your free body diagram? Now I know a lot of people in the room disagree with where those forces are placed. Okay? First of all, Daniel, the 2.23 newtons. Why did you put that where you put it?
That's the meter stick.
Yeah, but why put it in the middle? Because the meter stick was uniform. I said at the beginning you can assume the meter stick is uniform, right? So the weight goes in the geometrical middle. So that's the 50 centimeter mark. Everybody good? Okay, so let's see here. The 5.17 newtons. Who put that up? Kim?
Mm-hmm.
Kim, where's that located?
At the 10 centimeter mark.
Right, that's where the hanging mass is at. You have to put the force on the free body diagram where it's applied. Okay? The 7.4 newtons. Michael, where's that at?
The 22 centimeter mark.
Everybody good? And it's the sum of the other two forces. Now, why can we say, take 1 minute, figure out with the people at your table, Why can we say the normal force is 7.4 newtons? We didn't measure it. Go, figure it out with your people.
That's the weight of the.
Note the answer that is the sum of the other two forces is an insufficient rationale.
Also becomes not accelerated.
While it is true, it is not a reason. I need a reason.
It's not rotating it anymore.
Just like debate, an assertion is insufficient without supporting evidence.
That is not true in debate.
Oh, that is so true. What?
No, it is not.
Maybe that's why you lose rounds.
It's not true for our president.
All right. Let's just remember who beat you at Hockaday Octos. Okay?
I let you walk
No,
over
no,
me.
He did you a favor.
No, I did
Okay. Clearly we fooled around long enough. Who can give us an explanation for why the normal force needs to be the sum of the other two forces? Monray, what do you got?
Because the ring state is only place where a normal force could be acted on the meter state. Because it's the only place, it has to be the sum of the two forces because the meter state isn't moving.
That's, oh, you were so close. I need a physicsy word for moving.
It's equilibrium. It's not accelerating.
There we go. It's not accelerating. So the meter force is not accelerating. Okay, so this should be something everybody can finish off for me. Net force equals 0. There we go. In this case, net force equals 0 because the meter stick isn't accelerating. So if we have two downward forces, there has to be an upward force that's equal and opposite, right? Okay, there we go. Everybody good so far? Yeah. All right, so here's the next thing. What I'm going to ask you to do is determine the torque exerted on the meter stick by each of those three forces. We got the force part, right?
Yeah.
Okay? We need the R part. Everybody okay? Torque equals R cross F. We need the R part. So, here's how this works. What you have to do is choose an origin. Everybody okay? Where do I have to place the origin?
Center of gravity.
Geometric.
Center of gravity.
You don't have to place it anywhere.
Anywhere you want.
Anywhere you want.
Oh.
I meant,
That's right.
I know what you meant, Brandon.
Yes, thank you.
No, you don't.
Yes. Okay, to solve the problem, I can place the origin right there if I wanted. Right at the end of my fingertip, and this will work. It will be annoying, but it will work. R is what we call the torque arm. In the equation for torque, R is what we call the torque or lever arm. You're going to see both terms. You need to recognize them. It is the distance from the origin to where the force is applied.
It's the what?
Let me say that again. R is what we call the torque arm or the lever arm, and it is the distance from the origin to where the force is applied. Note, you can put the origin wherever you want. And you should get the same answer. If you get a different answer, then physics is not what we call spatially invariant, which means that the physics where I'm sitting is the same as the physics where Brandon's sitting. If the physics for our universe is different in different places, I quit. I'm going to go find a mountaintop and teach just TOK. No more of this physicsy stuff. I got to learn different physics for every. Think about it. Now, we can put this on a big, massive scale, which is what we usually do to make it obvious. The physics where we're at can't be different than the physics in the Andromeda Galaxy. But if the physics is different here than it is in the Andromeda Galaxy, then although it might not be measurable, it would also be different where I'm at and where Brandon's at, and that I'm not up for learning whole new physics for every different place we know.
But Mr. Lyons, isn't physics already spatially invariant because like classical physics on the macro level and then physics on the quantum level like are completely different?
How do you know?
Well, I mean, for example, like if I throw a ball at Qua's face, it's probably gonna hit him in the head, right? But if we were on the quantum level and I could somehow throw an electron at Qua, there's like a good chance the electron will just like teleport around him. No, I'm serious. Electrons teleport around their orbits within atoms.
I know, but what if it teleports back at you?
There's basically no chance or TVs wouldn't work.
Ooh. But
The
still.
TV you have now is not, but the TVs that I had growing up and the old-fashioned computer monitors, the ones that, there's a screen, and the screen is curved, and then the whole monitor goes back, and there's the back of the monitor. That's an electron gun.
But still.
It shoots electrons at the screen.
But still, classical physics break down at the quantum level. Doesn't that mean it's spatially invariant?
No, not necessarily.
Oh.
Sorry, nice try. Okay, all right, so what we need though is to make a wise choice about our origin. And we'll talk about wiser choices in a couple of minutes. But if I put my origin right, I feel like it should go here. There we go. Then this distance from here to here would be the R value for the weight of the hanging mass of binder clip. The distance from here to here would be the R value for the normal force. And the distance from here to here would be the R value for the weight of the meter stick. And on each of them, you would have a different angle as well. Shoot yourself in the face now. Or, I could put the origin, I choose not shoot self in face. I choose here. And I'm gonna label it O, for origin. Everybody good? So that is my origin, right there. Right at the 0 mark at the end of the meter stick. Aha. Everybody good? So here's what I want you to do right now. I want you to find torque values for these three. Torque for the hanging mass, torque for the normal force, and a torque value for the weight of the meter stick. Torque equals R cross F, and I set it up so that if I draw an R vector, let's see, new color, red. Here's my R vector from the origin to where the hanging mass at. What's the angle between them?
90 degrees.
20.
Pi halves radians.
90?
2.
Oh, like that. Okay, got it.
Oh, see what the angles between.
So weight acts
What
down.
the angle between the vectors.
The R value is horizontal. That makes the angle 90. What's the sine of 90? Okay, I'm not even answering that. If you don't know, you're in trouble. Okay, all right. Find the torque for each of those. Go. Double check with everybody at your table. Make sure you got it right.
Okay.
Work quickly because you have other stuff to do.
I don't understand how the torque value can be the same no matter what position you choose to be
The torque value won't be the same, but the result of what we're doing when we get to the end will be.
Oh, okay.
Trust
I was
me.
like, it doesn't make any sense how the torque value can be the
The
same.
torque values would all three be different, but when we're done with each of these three, we're going to add them. Just like we do net force, we're going to do net torque.
Force. Oh.
And the net torque will be the same regardless of what you choose to do.
Oh.
That's the way.
Okay? And there are easier places to put the origin, by the way. Go.
Yeah.
Just find the torques for the origin I've given you, which is not the easiest one, but it's easier than some.
Why do you keep saying it multiple times?
We have to change the